Hey everyone, welcome back to Algebra 2. Today we're going to be talking about probability. And specifically, how does describing events as mutually exclusive or independent affect how you define probabilities? But first, before we get into mutually exclusive and independent events, first we're going to go over some basic probability ideas. Some notation, just to make sure we're all on the same page, because it may have been a while since you've studied probability. Then we'll talk about mutually exclusive and independent. But most of your assignment will focus on the idea of mutually exclusive and independent events. You can follow along in section 12.1 in your volume 2 Algebra 2 workbook. All right, so the first thing that you need to know, and by the way, this won't appear in your workbook until we get to example 1, you won't see it. So you might need to write this down on your own paper or over to the side. But probability is the likelihood that an event will happen. And the way that we measure probability is we count the number of favorable outcomes In other words, if you're trying to find the chances, whatever you want to happen, out of the total number of outcomes. And that's how you find probability. It'll be represented by a number in between 0 and 1. If probability is 0, that event is not going to happen. 0 chance it will happen. If probability comes out to be 1, it's definitely going to happen. So probability will be represented by a number from 0 to 1 as a fraction, decimal, or percentage. There's some notation. We read this P of A is the probability that event A will occur. So if I were to look at this spinner, if you notice that the spinner is divided into 8 equal sections. So if I wanted to say, okay, well, I'm going to win this game if I spin the spinner and get a number less than 3. So let's say I wanted to find the probability of getting a number less than 3 on one spin. All right, so how many outcomes are there all together? Well, when I spin the spinner, it could land on a 1, it could land on a 2, a 3, a 4, a 5, it could land on a 6, a 7, or an 8. So there are 8 total things that could happen. But I will win whatever game it is if I get a number that's less than 3. So what numbers are less than 3 that are on the spinner? 2 is less than 3, and 1 is less than 3. So there are 2 ways that I can win out of 8 altogether. And 2 out of 8 reduces to 1/4. So the probability that I'll spin the spinner one time and get a number less than 3 is 1/4, or 25% chance. Now this other notation, probability of A with a C up in the exponent's place, we read this the probability of A complement, and that's the probability that that event will not occur. So you might see it written like this. You might just see like probability not A. You just might see it written out. Or you might also see it, some books do it like this with an A and a line over top. But our book does the A complement. So let's see. The probability that I get a number less than 3, well, I win if I get a number less than 3. So let's say the complement would be the probability less than 3 complement of that. So that pretty much means the probability that I will not get a number less than 3. So let me grab a different color. We know that when I spin the spinner, there's only 8 things that could happen. So now I need to count for probability that I won't get a number less than 3. Let me count those. That could be an 8. Oops. Could be an 8, a 7, a 6, a 5, a 4, or a 3, because 3 is not less than 3. So 1, 2, 3, 4, 5, 6. 6 ways out of 8 that I will not win. So if If I win the game by getting a number less than 3, I have a 25% chance of winning. If I lose the game, then I have a 6 out of 8 chance of winning, which is 3/4, or 75% chance of winning. So notice that these two, 25% and 75%, add to be 100. So anytime you're dealing with a complement, you can calculate the complement 2 ways. The first way is to look at it like we just did and still count up the number of favorable outcomes out of the total. Or if I know it's a complement, I can just subtract it from 1. So another way to say, if I knew the probability less than 3 complement, I could just take 1 minus whatever I had up here, 1/4, to get 3/4. You can do it either way. And you'll see those as we work through here. The other thing you need to know about is sample space. Sample space is a list of all possible outcomes that could happen for an event. So sometimes you'll see them as a list, sometimes you'll see them as a tree diagram, and then other times you'll see probabilities represented in a Venn diagram. If I have 1 die, and I rolled it 1 time, so roll once, 1 die, 1 time. Then all the things that could happen, I'll just make a list, and I'll call that the sample space. I could get a 1, a 2, a 3, a 4, a 5, or a 6. Those are all the possible things that could happen on a 6 standard die, 6-sided die. Roll them and get. Those are all things that could happen. Now, if I roll 2 die 1 time, or 2 dice once, there's a lot more possibilities, because the first number could be a 1 and the second number could be a 1. Or the first number could be a 1 and the second number could be a 2. Or a 1 and a 3. Or the first number could be a 1, second number could be a 4. First number could be a 1, second number could be a 5. The first number could be a 1, the second number could be a 6. Or the first number could be a 2 and the second one, and then a 2 and a 2, and then a 2 and a 3, and then a 2 and a 4. And I'm going to pause this and finish the sample space so you don't have to watch me list all of them. So now here's the entire sample space, or if I were to roll 2 dice 1 time. It's quite a big list, but it is helpful for me to find all different types of probabilities. So for example, what would be the probability of getting doubles? Doubles means you get the same number on each die. So I could get a 1 and a 1, 2 and a 2, 3 and a 3, 4 and a 4, 5 and a 5, and a 6 and a 6. So there's 6 ways I could get doubles out of how many outcomes are there? 1, 2, 3, 4, 5, 6 times 6, so 36, which is a 1 at 1/6 chance. Okay. You can also, instead of doing a Venn diagram, we can also do a tree diagram. So let me erase this. Let me try to pause it for a second. So a tree diagram is where you look at the probabilities as you go. So let's say on my first roll, what could happen? Well, I could get a 1, or a 2, or a 3, or a 4, or a 5, or a 6. Then what would happen next would be roll number 2. And so if I got a 1, then I can get another 1, another 2, then I could get a 2, or a 3, or a 4, or a 5, or a 6. Now I would do that. I would do 6 branches from each number, which for this example, it looks like a lot. And you can see that tree diagrams may be simple or complicated, but you just need to know that they exist. So that way, whenever it is convenient to look at them, you won't be blindsided and know, oh, what is this tree that we're doing? Because we will do some tree diagrams today. All right, so then we have multiple events. So multiple events are either and or. So let's say that we are going to play a game with this spinner again, and we will win this game if, let me write this down, we'll win if you get a 2 or an odd number. Now, an or, this is the first scenario, is if you have or. So it's the notation is probability of A, this U, which means union, B, or it can also be written A or B. So I'm going to say probability that I want to find the probability that I get a 2 or an odd number. Well, how many so remember I'm going to do the number of favorable outcomes. Favorable meaning like what you're trying to figure out the probability of, out of the total number of outcomes. Well, I know that there are 8 things that could happen when I spin the spinner. I can land on the numbers 1 through 8. But I win, the favorable outcomes for this scenario would be if you get a 2 or an odd. So I'm going to look, and every time I see a 2 or an odd number, I'm going to label it as favorable. So 1 is odd, and there's 2. 3 is not 2, but it's odd. Let's see. 4 is not 2 or odd, but 5 is odd. 6 is not 2 or odd, but 7 is odd. And 8's not 2 or odd. So there are 1, 2, 3, 4, 5 sections that I could land on that would either be 2 or odd, and then I have a 5/8 chance of winning this game. Well, if instead of me winning with the 2 or odd, if we change this little word or to the word and, then there's a big difference. So let's say I would win if I landed on the 2 and an odd number. So in order for me to win, we know, by the way, that there are 8 outcomes total. In order for me to win, the section that my spinner would land on would have to meet both criteria. It wouldn't have to meet just one. It would have to meet both, being 2 and odd. Where's my, okay. So let's see which fall in those category. 1 is odd, but it's not 2. So that's not an option. 2 is 2, but it's not odd. 3 is odd, but it's not 2. 4 is not odd. 5 is odd, but it's not 2. 6 is not odd. 7 is odd, but it's also not 2. And 8 is not 2. So there are actually 0 ways of getting a number that's 2, both 2 and odd at the same time. So there's a 0 chance that I'll win if we change the word or to and. And if you're like, well, that doesn't seem very fair. Well, that leads us to something called mutually exclusive events. Mutually exclusive events are events that have no outcomes in common and can never happen simultaneously. So like the spinner right here, events that cannot happen simultaneously would be the one we just talked about, 2 and odd. I can never spin the spinner one time and land on both 2 and odd together. Here's a Venn diagram that would kind of show what was happening. So let's let this block A be the 2s and B be the odds. And so the way you would read probability within a Venn diagram would be you would look at, okay, I would write the probability of getting a 2, the probability of getting an odd, and see if they would ever overlap. So the probability of getting a 2 is 1 out of 8. And I would just label it here. The probability of getting an odd, 1, 2, 3, 4 out of 8, which is 1/2. And then on the outside, the probability of none of that happening, 1, oh wait, already 2 is that 1/8 is right here. Let me get a blue. Okay. 1, 2, 3. 3 out of 8. So Venn diagrams are also one way that we'll look at probability. It also allows us to see if any probabilities overlap as well. But mutually exclusive, those events cannot happen together. So now if you look in your workbook, we can start working some of those examples. So example 1 says that a box contains 100 balls. I'm looking for my notes here. There we go. They're just written so lightly. Okay. Box contains 100 balls. 30 of the balls are purple and 10 are orange. If you select one of the balls at random, what is the probability that of each of the following events? So I want to know the probability that the ball is purple or orange. Okay. Probability the ball is purple or, I'm going to use the union, orange. Okay, so remember, we're doing the number of favorable divided by the total number of events, or total number of outcomes. So how many balls are we picking out? No, this is not an accurate picture, but how many balls are we picking out of this box? We're picking 1 at random. How many are there total? There's 100. So there's total 100 outcomes possible. How many of those are favorable? Let's see. There are 30 purple and 10 are orange. So I would win if I get a purple or an orange ball. So that would be 30 plus 10, 40 out of 10, which is 4/10 or 2/5. Okay, this is part B. Probability that the ball is purple, not purple, and not orange. Oh, you might also see it like this. You might also see the complement symbol as just a hyphen, not a hyphen. What is that word? Not a hyphen, an apostrophe. So not purple and not orange. Okay, so not purple and not orange. Okay, well, I know the probability of getting a purple and an orange is 2/5. So not purple and orange would be everything else. So I could do 1 minus 2/5 to get 3/5. That's one option. Other option is to say, well, I know there's 100. I know that 40 of them are purple and orange, so that makes 60 purple or orange, 60 of them not, which is also 3/5. Either of those, the same. Now, what were to happen if I were to ask you for the probability of getting a ball that is both purple and orange? Well, we don't really have enough information here because we just know that there's 30 purple balls and 10 orange. We don't know if there's any multicolored balls, but if they're all single colored balls, like what would be in the ball pit, that are only one color, and let's assume that that's what's happening here. If a ball can only be one color, then it wouldn't be able to be purple and orange at the same time. So we would say 0 out of 100, because in this scenario, if we're considering that the balls can only be one color each, then these events would be mutually exclusive. So here's a couple extra examples just to work on mutually exclusive. So example, a cooler contains 20 bottles made up of 8 Cokes, 5 Pepsis, and 7 waters. The probability that you would choose a Coke or a Pepsi, is there any time that Cokes and Pepsi would overlap? No, because whenever you pull a bottle of Coke or Pepsi or water out of the cooler, it's not both. It's either one or the other. So if I were to do that out of 20, I would say there are 8 Cokes plus 5 Pepsis, which would be 13 out of 20. Parking lot contains 20 American cars, 40 Japanese cars, and 35 German cars. The probability of choosing a foreign car is foreign, assuming that foreign would just be not American made. Let's see, how many cars are there altogether? 20 plus 40 plus 35. 60, 95. And so how many foreign? Let's see, 40 plus 35, 75 out of 95. All right, non-mutually exclusive events are events that can happen simultaneously. So here's an example. This is not in your workbook, but it might help show this a little bit better. So what's the relationship between educational achievement and home ownership? Random sample of 500 U.S. adults was selected. Each member of the sample was identified as a high school graduate or not, and as a homeowner or not. The two-way table displays the data. Suppose we chose a member of the sample at random and define the events. So G would be person being a high school graduate, H is person being a homeowner, and this is just helping with notation. Now, how does this help us understand non-mutually exclusive events? Well, are G and H non-mutually exclusive? Can you be a high school graduate and a homeowner at the same time, according to this data? So these are the high school graduates. These are the homeowners. So can you be a high school graduate and homeowner in this data? Of course, yes. 221 people were both high school graduates and homeowners at the same time. So yes. Can you be not a high school graduate and a homeowner at the same time? Not a high school graduate and a homeowner? Yes. You can. 119 people were that as well. All right, so let's look at some examples from your book. This is example 2. Find the probability of non-mutually exclusive events. A video game is played on a 34 centimeter by 20 centimeter rectangular screen. Okay, so I'm going to go ahead and draw a rectangle. And by the way, it's computer screen. I believe that's more like a Game Boy size screen, but whatever, we'll go with it. Okay. We'll say this is 34 centimeters, and this is 20 centimeters. Starship is represented by 2 overlapping circles of radius 6 centimeters, whose area of overlap is 20 centimeters. So let me draw some circles here. It says they both have the same radius. So let me just duplicate this. There we go. And it says that their area of overlap is 20 square centimeters. Okay. Black hole is equally likely to appear at any point on the screen. So that means a black hole could appear here, could appear here, 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 equally likely anywhere on the screen. To the nearest whole percent, what is the probability that the point will appear within the starship? Within the starship. So this is one whole starship. Okay. So what's the probability that the black hole would appear anywhere in here? So it can appear here, 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 and it would still land within the starship. All right. So this would be, let's call this circle A. Let's call this circle B. And with notation, what we're asking for is we're wanting the probability that the black hole would land in circle A or in circle B. Now these events are non-mutually exclusive. because the black hole could land in starship A, could land in B, but it could also land in A or B. And so the fact that it could land in a section that they're covered by both makes these two events non-mutually exclusive because they can happen at the same time. So we do have a formula for this, for non-mutually exclusive events. If A and B are not mutually exclusive events, and you want to know the probability of A or B, then you find the probability of A, which is shown by this orange circle. So it kind of helps if I color it in. So probability of A would be like all of this. Coloring in, so that would be the probability of A, plus the probability of B, but you see how I have, plus probability of B, but I have colored in this, let me grab a different color. I've colored in this overlap twice. So I need to subtract one of those away. So I need to subtract like maybe the blue, so I don't count it twice. Because otherwise, if you don't subtract the probability of A and B together, then I'll be counting it twice. So let's look at this one. So if I want the probability of A or B, then I'm going to need to find the probability of A plus the probability the black hole lands in circle B minus the probability that it lands in both. All right, so the probability that the black hole would land in circle A would be the area of this circle. And the area of a circle is pi r squared. And we know that the radius is 6 centimeters. So pi times 6 squared would be 36 pi. So 36 pi is the area of this circle right here. And remember, probability, it's the favorable, and in this case, since it's talking about area, the favorable area divided by the total area. So now I need to figure out what's the total area. So the total area is the area of the rectangle, which would be 20 times 34, and 20 times 34 is 680. Plus, circle B has the same radius, so I can say 36 pi over 680 minus, now I need to find the probability of A and B. I need that area of overlap. Now the probability, wait, let me just make sure I'm actually recording here. Yes, sorry. The probability that they overlap is given to us in the problem. Area of overlap is 20, so 20 centimeters out of 680. So I'll do all this, I'll subtract, I'll add it together and then subtract. Make sure whenever you type this in your calculator that you put 36 pi in parentheses. But when you do this, you should get about 0.3 or 30%. 30% chance that a black hole landing anywhere will actually land on the starship. All right, example. Oh, so and once again, this probability, the formula for finding the probability of non-mutually exclusive events. If you're finding the probability of mutually exclusive events, events that can't happen at the same time, you can do it similarly. Probability of A or B would be the probability of A plus the probability of the second event. And then for mutually exclusive or non-mutually exclusive events, you have to subtract the probability of A and B happening together. You don't have to subtract it for mutually exclusive because remember we said that the probability of A and B happening together is 0. So we don't have to subtract it out. All right, now let's talk about independence. Independence means is that two events are independent if knowing that one event occurs doesn't change the probability of the other event occurring. So with independence, we're thinking more of like two things happening. So for example, tossing one coin and then another coin are independent of events, or even the same coin over and over. So let's say I have a coin, it's got a heads on one side, tails on the other, and then if I toss another coin, it's got a heads on one side and tails on another. Well, let's make that tree diagram. So toss one. Two things that could happen. I get a head, tails, or a heads. The probability of getting a tails is 1/2. The probability of getting a heads is 1/2. Now, if I get a tails, my second toss, I could get a tails or a heads, or another tails or a heads. Now, I got a tails on the first toss. The second coin, the second probability is not affected by the first one, so that probability remains 1/2. The fact that this remains 1/2 and is not changed by what happened in the first event, that's what makes these two events independent. So then let's look at example 3. There are 10 cards in a box, 5 black and 5 red. 2 cards are selected from the box one at a time. So I'm going to pause it and draw this out. Okay, so I've got my cards here, 5 black, 5 red. 2 cards are going to be selected. So for part A, card is chosen at random and then replaced, and another card is chosen. Does the color of the first card chosen affect the probabilities of the second? Okay, so let's say I have my first card. Two things can happen. I can either get a black card or I can get a red card. Chances of getting a black card, there's 5 out of 10. And I'm going to leave it 5 out of 10. Leaving the fractions unsimplified in your diagrams does help you spot the overall probability. And also, especially like adding probabilities makes it easier if all the denominators are 10. Okay, then red, there are 1, 2, 3, 4, 5 reds out of 10 altogether. Now on my now I take a card, but then what does it say I do? It's replace. So that means I take a card away, but then, I put it back. So still, if I put it back, then that means there's still 10 cards in the lot. Okay, so then if I draw a black card, I can get either a black or a red. And then if I draw a red card, I can still get a black or red. Replacing everything means that these probabilities are going to stay the same. They do not change whatsoever. So does the color of the first card chosen affect the possibilities of the second card chosen? No, it does not, because the cards are replaced. Which means each draw is independent. Now let's look at B. This time a card is chosen at random and not replaced. We don't know what color it is, but we can make a diagram. So let's make a tree diagram. Might have a red card or a black card. Now there's still 5 red cards and 5 black cards at the beginning on my first draw. So I have 5 chances out of 10 of getting a red and 5 chances out of 10 of getting a black. But I could then draw a black or a red again. But there's no longer 10 cards in the deck because they're not replaced. There's only 9 left. Now if I drew a red and took it away, then there would still be 5 black cards left. But if I drew a red and took it away, there would only be 4 red cards left. So you see how these probabilities are changing? Now let's look at what if we drew a black card first. B for black, R for red. If I drew a card and did not replace it, that would mean there's only 9 cards left for the second draw. And let's see, if I drew a black card first and did not put it back, there would only be 4 black cards left, but there would still be 5 red cards left. So do you see how these probabilities are changing? So that means to say, does the color of the first card chosen affect the possibilities of the second card? Yes. The card was not replaced. These events are not independent. Probability of one does affect the probability of the next. All right, and here's just a glance. So take a second and read through this. And it is, you will see probabilities written as fractions, decimals, or percents, but the form will change based on what's convenient for you. All right, so last example, you spin a spinner 2 times. Assume that the probability of landing on the blue is 1/3 and the probability of landing on the orange is 2/3. What's the probability of getting the same color both times? Let's see. Here's another example where a tree diagram would work nicely, and I'm going to need a little more space. There we go. All right, so then on my first spin, I could either get a blue or I can get an orange. Now, spinning a blue, we said the probability of getting a blue is 1/3, and the probability of getting an orange is 2/3. Now, I'm spinning the spinner on every time I spin the spinner, the areas of those regions are not going to change. So it looks like these are independent events here because these probabilities are still going to be the same. So 1/3 for blue, 2/3 for orange, blue, and orange. So 1/3 for blue, 2/3 chance for orange. All right, then it says, what's the probability of getting the same color both times? So there's a couple ways this could happen. Highlight the path. Same color both times would be me getting a blue and a blue, or me getting an orange and an orange. So the tree is really helpful here. So to get a blue and a blue, I would have to do 1/3 times times a third equals 1/9. That is the probability of getting, I can just erase that. That's the probability of getting 2 blues. Okay, to get 2 oranges, I would take 2/3, multiply it by 2/3, we get 4/9, which is the probability of getting 2 oranges. Now, if I want to know the probability of getting just the same color, so either one, then I just add those two together. So the probability of getting 2 blues or 2 oranges is 1/9 plus 4/9, and I don't have to subtract any because you can't be blue and orange at the same time, 5/9. So 5/9 as my total answer.